the idea of that presentation today is to talk about design and of and with next generation machine elements. Question is, what are the design challenges ahead of us? And this reflects to a project which we had in Germany for the last more than 2 years to arrange a research program which is officially funded. We're just in the process, everybody keeping our fingers crossed that we get our applications approved. We're waiting for the news from the Deutsche Forschungsgemeinschaft in Bonn in, I think it's 2 months from now, about the funding decisions. And then we will start to develop those next generation machine elements within the special research program on a similar topic. I just have seen also Thomas Grosch being in the call. Thomas was also a part of the team when we started that application process. And our plan is also to make that more international. That's how I came to this talk, having presented in January, also in the design theory SIG of the Design Society. And this is now a little bit enhanced version of that presentation, or modified version. First question is, why do we need to bother about machine elements? Many people claim that machine elements, that's ancient stuff. Everything that needs to be said has been said about machine elements. Okay, probably they're right, but I'm trying to counterprove them. I will try to prove them wrong and show that there is indeed a lot of things happening. First, looking into the history, no pyramids without rolling bearings. If you look to that picture, you will see that there's a payload on a carrying sledge. We have a lubricant here. We have a guiding track, and we have rolling elements to move the stone blocks on that slope in order to build the pyramid. Next piece of evidence that machine elements are really important. The bearing here in the middle was the key factor that made the idea of the wheel becoming an invention. Imagine the wheel without the bearing. It would be almost useless. Looking 4,000 years back. When we look to the automobile, also there we see a big increase in technology. The first automobiles, here the ancient vehicle of Gottfried Daimler and the Benz, they were enabled by the industrially available rolling bearings 140 years ago. The idea to counterproof is probably here the older ones of us, and I count myself to belong to that older group. Meanwhile, we can still remember the movie from the 80s, Back to the Future. And here that DeLorean, which is barely driving, it's flying. But if we look to that vehicle, we see that here we still have the tire. But in order also to establish that kind of vehicle, we still need some kind of a rolling bearing or some rolling elements which supports the wheel while rotating. So even though it looks as if no more machine elements were required, we still need them. Also the Perseverance moving on Mars, it's enabled by rolling bearings and machine elements indeed. Looking to the gears, also gears and spur gears have a long history from wooden arrangements. Why are the first industrially produced vehicles? They're very simple. Here, transmission still yet with a helical toothing. We look carefully to that. And now there's many people claiming, when we drive electric, we don't need a transmission. But even with the Tesla, we need a transmission. And out of my industrial experience, Oscar mentioned that, I know that developing such a simple, non-shiftable transmission is as complex as developing a 6-speed manual transmission where you have all that engine noise, which is masking the transmission noise. So it's still very difficult, and we need to keep pace with the development of those components. If you look, for instance, here to the electric machine, operated at 20,000, 25,000 RPM as a target for the next couple of years, we will all of a sudden recognize that we are lacking bearings, we are lacking sealings, we are lacking the technology to produce the gears, but there's still a lot of things to do ahead of us. And this is just talking about what I will mention or call in the next slides, the conventional machine element area, and not yet talking about the challenges which arise out of the overall present digitalization process, which is putting us all under pressure. So let's start to look to the machine elements and try to somehow classify those. Machine elements, there's numerous textbooks, but if we look carefully, they are all on the conventional machine elements, which we know from our education: bolts, bearings, journal bearings, couplings, shafts, connection pieces, etc. Now we see in the research over the last couple of years that something called mechatronic machine elements is cropping up. We have dug into the idea, and we discovered that we have to distinguish between actoric machine elements, so even being able to somehow perform an action inside the machine element. And we have sensing machine elements. We will focus on the sensing machine elements for the time being, just for the very simple fact that it's hard enough to bring the energy for a sensor into the machine element. If we manage that, if we have understood that, we can start about getting the energy for an actuator into a machine element. It's again one order of magnitude higher energy requirement, which is increasing complexity. First, we want to solve the sensing machine elements. And now when starting to discuss about machine elements as a sensor, we will very quickly figure out that there's different ways to accomplish that. We can, as the most simple case probably, establish a sensor carrying machine element. I will get into the differentiation on the next slide. We try to find a terminology that is somehow self-explaining. Here it says sensor carrying machine element. The machine element carries a sensor. We have sensor integrating machine elements. Okay, there's obviously a difference. Here we have only a sensor. Now it's integrating. The machine element integrates the sensor, and that means also that we have to somehow include also some intelligence, some way to communicate between the sensor and a control system. That all needs to be included in the machine element. And the third group, however, is what we call sensory utilizable machine elements. This machine element includes an effect which can be somehow used as a sensor. Best example here is a rolling bearing. During the last ISET in Delft, in 2019, we got that little bag. When I looked into that bag, I found that little rolling bearing. I said, hey guys, look, it's cool, there's a sensor. But obviously I was the only one who saw that. The rolling bearing, it has a tribological system included, and that changes its properties, its electric properties with speed, temperature, and load. So we can use it as a sensor. It's still research topic. It's not yet at a maturity level that we can use it in industrial applications, but the sensor system is proven, it works, but it's still a long way to go ahead of us. Let's look to the details. We have the sensor carrying machine element. We have our mechanical function and the electrical sensing function. They are being independent of each other. The machine element just carries the sensor. There is no interaction between the two of them. The example here is a bolt with an integrated thermocouple. The bolt measures the temperature independent of the bolt force. And it works also when we just put the temperature onto our desk and connect it. It doesn't need to be installed, integrated into the system, just recording temperature. The next concept, the next group, the sensor integrating machine elements, there we have a connection between the mechanical function of our machine element and the signal provided. The example here is a sensor integrating feather key. We attached strain gauges to the top faces of the feather key. With that strain gauge, we were able to measure basically the deformation of the feather key, and that led us to the conclusion on the torque acting on the shaft hub connection. We have a direct relation between our sensor signal and the mechanical load of the feather key. The sensory utilizable machine elements that we can't really distinguish between the mechanical function and the signal generation. It's basically a part of the machine element which is used as a sensor. And here the example shown is a journal bearing, hydrodynamic journal bearing. The idea is we have here an insulating fluid between our journal bearing and the shaft, and that fluid film can be interpreted as a somehow distorted cylindrical capacitor. When we start to move that shaft with respect to the bearing shell, we're changing the capacity, and that can be used to again calculate backwards, first on the position of the shaft, and from the position we can, when we utilize the journal bearing theory, we can deduct the force acting on the bearing. But that's the idea. Let's look to the example of a sensor integrating tooth belt. Tooth belts are a fairly new machine element. We have an active project with a tooth belt supplier. And the idea was, how can we make that tooth belt survive the current evolution of the mechanical design, make it somehow fit for the future, make it fit for digitalization, and include a sensor. This was our idea. Take one of the teeth here. We simply integrate a sensor. This is a whole chip that can be integrated into the tooth. We see here the dimensions. A euro coin gives you an impression of the size of that prototype. And here for the first prototype, we have the sensor module, and then the neighboring tooth, we have the battery. We have our tooth belt. The width is approximately 50 millimeters. It has a ultimate load carrying capacity of around about 50 kilonewton. So it's really a high performance tooth belt. It cannot be compared with the tooth belt which we know from our combustion engines, used for a timing belt. This is a high performance belt, and we see here we have steel strings inside that tooth belt. The steel strings, they deteriorate with usage time. The stiffness changes, and with that, the force inside the tooth will change. In order to measure the span-specific forces inside that tooth belt, we applied 2 accelerometers to that sensor chip here. And the accelerometers, they provide a voltage. From that, we can conclude to the eigenfrequencies, to the frequency level. And via the string equation, we can calculate backwards to the force acting on the tooth belt depending on its position inside the belt drive system. Here, as mentioned, the lithium polymer battery, I've just confused the sequence here with the battery, here with the sensor. We have a Bluetooth transmitter included, so that system is able to communicate out of the rotating system. We have to provide energy to the sensor module, that's the trick here of that system, to get the energy to the chip without interfering with the rotating tooth belt. And here I need to be somehow tight-lipped because the patent applications are not yet finally concluded. I cannot go into the details without violating the confidentiality agreement with our partner. I need to confess that here. The system works on the prototype status, but we have to overcome some hurdles. We will see later on that temperature plays an important role. We have also integrated a temperature sensor. So with recording the temperature, we can eliminate the thermal effects which cause disturbances in the signal recorded and the signal delivered to our processing unit. Let's look to the challenges of that system. First, we all know the tendency of our smartphones. If we allow them to drop from 1 meter to the bottom, the smartphone experiences an acceleration event of around about 500 G, 500 times the natural gravity. And we all know if we do that too often, we will get that popular spider app to our smartphone, and the smartphone is gone, the screen is broken. Now we use the sensor technology, which is included in those consumer products and which are produced on a 100 to million units scale. If you want to use those sensor components in our timing belt, all of a sudden face enormous problems. We have here our peak loading event to the sensor, 500 G. If we look to the Euler diagram for such a component, we see, okay, we are somehow here in the short low cycle fatigue area. When we compare that with a tooth belt, we will all of a sudden see that 500 G, that's almost nothing for a tooth belt. If we imagine a belt passing a disc with 100 millimeters diameter at a speed of 3000 revolutions per minute, that's 50 revolutions per second, yet causes a 500 G event. And that anytime the tooth belt or our specific belt with a sensor passes through one of those discs. Here we see in that example, we have 7 discs. So once the belt rotates as a whole, we have 7 load events. At high speeds, here assuming 3000 RPM, we have 50 revolutions of the disk. That means we have, I don't know, a couple of 100 loading events per minute, or even more. A couple thousand loading events per hour means our durability limit is exceeded within a day, if even. So we have to improve the sensing technology, the microelectronic components, in order to be able to withstand the load profiles in those machine element applications. So we have to strengthen the components to withstand not that grayish a load profile, but the black or even more severe load profiles in order to make them survive the application. An extreme but not unrealistic example is if you take the same belt, and now we have a speed of 9,500 RPM at our disk. We have a centrifugal acceleration of 5,000 G acting on that sensor component. This is probably not yet the limit, but it shows that we have to expect extreme loading conditions. Knowing that a acceleration sensor has a saturation threshold, typically in the area of 400, 500, or even 1000 G, we know that we have to struggle with the case that we have in big portions of the operational scheme, we are almost blind. As soon as the sensor passes through one of the disks, the acceleration exceeds the threshold value, and we can't read anything from that. We just go into saturation. So we have to sort out all those problems. Let's look to them some examples. And here we have to have the understanding of uncertainty in mind. This is affected by our special research collaboration center here in Darmstadt, SFB 805, managing uncertainty in load carrying systems. Uncertainty is a state, even partial, of deficiency of information related to understanding or knowledge of an event, its consequence or likelihood. So we see that uncertainty is, in many cases, affecting the design of and with those sensing machine elements. Let's look to an example. We have a disturbance variable, the temperature. The temperature change causes a thermal expansion, for instance, of our tooth belt. Here, the thermal expansion of the steel wires is the dominating factor. And that leads to a change in eigenfrequency. If the steel, the wires elongate due to thermal expansion, the pretension will drop down, or at least change the length. So have different influencing factors on the eigenfrequencies and on this measured signal. Including now the temperature sensor helps us to eliminate at least the effect of the thermal expansion. We can somehow try to compensate the difference in the eigenfrequency due to the thermal condition. But if you now start to think about a simple two-disc belt drive, you know probably from basic machine element courses that there's a version where we have a dead load. We just pretension the system, keep it as it is. And we start to do some Gedanken experiment. What happens with the thermal changes? We see all of a sudden that for this configuration, the temperature change is fairly high. The temperature effect. The belt elongates, it loses its pretension. We have a fairly high impact on the signal recorded. If we take the same belt drive and apply a static pretensioning force to one of the pulleys, we have a constant force. The thermal expansion is compensated by that spring-loaded pulley. We have a far lower change in the eigenfrequency, now not due to the force change, but to the length change. And it's a much lower influencing factor. So more stable with regard to the thermal effects is the system with the spring load on one pulley. For the system with the two rigid discs, we have a more pronounced change, and probably it's easier to detect changes with that system because we have a much higher sensitivity with regard to thermal influences. We have to decide which is the appropriate system to use in our mechanical design in order to be able to really understand what is the measuring task, what is the right design approach to handle that task. What are the challenges and opportunities of next generation machine elements? If we have those sensing machine elements, they will of course decrease the barrier for measuring tasks, and by that also speed up strategies such as Industry 4.0 and the whole digitalization process. The integration of sensory functions can be accomplished without the need to somehow package an additional sensor. The utilization of standardized parts leads to a less complex implementation of the sensor and also facilitates concepts such as the cyber-physical or digital twin system, which is currently under investigation. If we have understood how to manipulate and redesign the machine elements, we can transfer that knowledge to other construction elements. Pretty straightforward. And we have the ability also to split up a cyber-physical system, say a big transmission in an industrial plant, into several sub-cyber-physical systems with less complex models, resulting also in less complexity of the whole system, since we just pull together not a cyber-physical system of a transmission, we just assemble the cyber-physical systems of the shafts and make that a transmission. The in situ position of the machine elements also shortens the transmission path from the quantity of interest to our sensor. We can now basically apply, if we have those machine elements, the sensor directly into the process. We will be really measure at in situ positions. The drawback, of course, there is one. The technology readiness level of those machine element concepts is still very low. I just had a discussion with one of my research associates about the technology readiness level of that tooth belt system. It's still low. We are on the prototype status. The data transmission, for instance, out of that rotating encapsulated system is still a hard challenge ahead of us. I was hesitant to say unrealistic, but it's a hard question to get the data transmitted. Many cases permit the application of cables. So we have to find ways to supply the energy to the sensor and to transfer the data out from the sensor. In many cases without cables. So we have to find ways to operate the sensors with a minimum energy requirement operation strategy. We need to be able to send them to hibernation, wake them up in case something happened. That's the challenges which are ahead of us. The future research topics. How can we design the sensor integrating machine elements or next generation machine elements with a maximum autonomy of their energy balance? They need to somehow be able to survive not only 10 minutes of operation, but in industrial application, years of application at awkward positions. What design opportunities exist for the data transfer from a shielded position somewhere deep in a transmission or in a plant to the system controller, which is at a remote, a nice and cozy office location. We designed here that innovation radar. It shows here on the horizontal axis the gap to market maturity. So here we have a short here we are in basic research. So we have to think about how can we really make that system work? What is the effects to deploy? Here we are in pre-competitive research. And here we are ready for market. So there are very few systems which are really ready for market. We see here a sensor bearing. That's a rolling bearing with an additional integrated or added sensing layer. It's increasing the build length. And we see here that cable will cause a lot of trouble when integrating that, for instance, into a Vehicle application, it's close to impossible. Here's our tooth belt. And we see that the technology readiness level corresponds to the color shown for those concepts. Now the feather key is very low. We have applications which are ready for market, but both come with a cable. So we have to think about the ideas. We have to also chew on the fact that we need to somehow be able to redeploy modules and components from one sensor concept to the other, that we do not need to reinvent the components every time we start to think about next generation machine elements. How can we achieve a unique signal transfer path when we want to use the mechanical structure not only to transfer torque and power, but also to transfer signals? And how can we expand the three basic rules of engineering design? Simple, unique, and safe. How can we make them compatible with the future? Also think about unique signal transfer, for instance. So we see that there's a lot of questions ahead of us. And with that, I would like to say thank you for your attention. And I'm looking forward to the discussion ahead of us. Curious to your comments and view on that issue. Thank you.